Okay, welcome everybody. Welcome to our EOL seminar. Today's speaker is Gijs de Boer from NOAA and CERES, NOAA PhD and CERES. Let me tell you a little bit about his background. He studied atmospheric science with a bachelor from Cornell back in 2002, and then he moved to University of Wisconsin, Madison, where he got both his master's and his PhD. Part of his PhD thesis was Arctic clouds, aerosol cloud interactions, Arctic climate, and that eventually brought him into the UAV business. He actually had a postdoc then at Berkeley Lab, where was a bunch of modeling, right, but also this cloud activities. And, well, that's why we asked him to come here and tell us about his UAV work. He's very active in this, all the way from small to really big ones. I actually heard you were at the Shout campaign as well, right? So working on the Global Hawk. But today he's going to tell us about recent efforts to use small unmanned aircraft in studying the Arctic atmosphere. Please welcome Gijs de Boer.
All right, thanks, Holger. Thank you, everybody. So yes, as Holger said, I'm Gijs de Boer from the University of Colorado in NOAA, and I'm going to give a little bit of introduction into how I got into this UAV thing in the first place, and I will say that it's been somewhat of a winding road, but a good one, and hopefully people will agree that it's interesting. There aren't a ton of names on the screen, obviously. That's not to say nobody helped me to get through all the work that I'm going to show you. In fact, if I had to put the names on there, you wouldn't see any of the picture that's in the background. There's been a wide variety of people that have supported some of these ideas and some of the work that I've done here, and I'll do my best to recognize those people as I get to the kind of relevant portions of the presentation. So as was mentioned in the introduction, my background, when I was at the University of Wisconsin, I became very interested in Arctic clouds, and this happened somewhat, I wouldn't say by accident, but somewhat directly as a result of the fact that we had an instrument that went to the Arctic. I was working with the University of Wisconsin LiDAR group at the time, Ed Elorante, who some of you may know, and he had just kind of developed the first version of his high spectral resolution LiDAR that was being deployed to Barrow, and so we had this great data set coming in, and as an eager young master's student, I said, okay, well, we've got data, that's a good start, let's dive into that. And I became fascinated by kind of this scene. What you're looking at here is the HSRL's view of what is a mixed phase, single layer stratiform cloud. These clouds happen very frequently at high latitudes. Mixed phase meaning you've got a liquid component to the cloud and ice forming within that liquid and generally precipitating out of the cloud. And so you see here this area of high backscatter in the red is the liquid part of the cloud, and then all these yellow streaks that you see coming out of the bottom are the ice crystals falling out of the cloud. And part of the reason I became really interested in these things is they have these really extended lifetimes. This is one 12-hour period where there's very little variability in the cloud itself, but we've seen similar pictures lasting several days at a time. And when you put all of that into perspective, ultimately having that cloud in place for an extended time period has a substantial impact on the surface energy budget. The cloud itself is reflecting shortwave radiation. It also has an impact on the longwave side. And so this is a figure that shows a little bit of that influence. This is actually a year's worth of cloud radiative forcing from measurements from the Sheba campaign. This was an icebreaker that was floating around in the Beaufort Sea area. And this is from a paper by Matt Shoup and Janet Intrieri from about 10 years ago. And it shows the long-wave cloud radiative forcing, the short-wave cloud radiative forcing, and then the net forcing for all of the clouds in the solid line, the liquid-containing clouds in the dashed line, and then the clouds without liquid in the dashed dot line. And a couple things jump out here. One, if you look at the net forcing, generally these clouds are acting to warm the surface of the Earth at high latitudes. That's a little bit counter to what you might see at lower latitudes, where the key component is the fact that they're reflecting sunlight back to space. Here it's actually the long wave that's contributing most strongly for much of the year because, well, half the year you don't have any sunlight, so that part is somewhat irrelevant at that time. The other thing that jumps out is when you look at this, the liquid-containing clouds really are the dominant player in this net impact. And you see the dashed line fairly closely follows the solid line for most parts of the year. And so when you have these mixed phase clouds that are hanging around for days at a time, up to a couple weeks, and they occur quite frequently, that has a very strong impact on the energy transfer at the surface of the Earth. And so I became pretty interested in all the kind of physical processes that go into maintaining these clouds. The fact that you have ice and liquid existing together for long time periods, which thermodynamically is not a very stable environment, right? Ice should be forming kind of at the expense of liquid. It has a lower saturation vapor pressure. So why does that happen? How can the cloud maintain this balance with multiple phases at the same time? And in 2012, I worked with Hugh Morrison, who many of you might know, to put together a nice review paper on some of the pieces that go into maintaining these cloud layers. And it's a fairly complex picture. Things like radiation are important. Their cooling at cloud top is ultimately what drives a lot of the circulations in the cloud. You have this kind of cloud top driven convection, essentially upside down convection. You have the microphysics itself. So again, this interaction between the liquid and the ice, and kind of how that plays on the local aerosol population. You have the dynamics, so again, these cloud-driven circulations as well as the large-scale advection and the subsidence in this environment. And then you have the interactions with the surface, whether the cloud is mixing down to the surface, and whether, what the surface fluxes look like, so what the kind of contributions of moisture and heat are from the surface itself. And all of these things together can lead to the life cycle or the persistence of these cloud structures. And so, from our observational perspective, we have some interesting ways to look at some of this stuff. Oftentimes in the Arctic especially, we have these fixed sites, super sites that have a wide variety of really nice instruments, generally cloud radars, LIDARs, radiometers, interferometers. You have aerosol measurements, and you have an ability to retrieve the cloud properties using retrievals from the remote sensors. You have an ability to look at the radiative impact with surface-based radiation measurements. You have some information on what the aerosol population looks like from ground-based aerosol measurements. And you might have a few towers measuring turbulent fluxes at the surface. And so you get some pieces of this picture. On the flip side, there are some things that we are still missing. So one thing I think that becomes quite critical is, what does one flux tower mean when you're thinking about a surface type which is quite heterogeneous. You have up in the Arctic, you have a tundra, which tundra is not tundra. Tundra is not the same all over the place. You have some areas that are quite wet. You have some areas that are quite dry. You have seasonally, you have variability in surface moisture, in snow cover, things like this. And so if you have one tower sitting there providing you with information to develop retrievals or develop parameterizations to model this sort of stuff, you have to wonder how spatially representative the information from that tower is. Another thing has to do with the kind of vertical structure. And so we have all these measurements at the surface, and sure, we can do some retrievals with remote sensors. But for example, aerosol properties, there's a lot of question about how representative aerosol measurements made at the surface at high latitudes really are for things like cloud aerosol interactions, or just understanding what sort of particles these the cloud droplets and ice crystals are forming on. And this is particularly true at high latitudes because we know that there are quite frequently these stratified layers in the atmosphere. You have kind of inversions, stable areas, stable atmospheres. And so it's not directly obvious that the surface measurements that are being made are applicable to the cloud layer itself. And so I started thinking about how can we get at information in a different kind of set of observation, using a different set of observational tools. How can we get at some of the dimensionality that I just discussed? And there are, of course, manned aircraft, which have provided useful information from a variety of research campaigns in the Arctic. And there are unmanned aircraft. And the CU has a very strong history in the use of unmanned aircraft, I would say. And this is true in the Arctic as well as other parts of the globe. Starting in the early 2000s, there were several groups on campus that used unmanned aircraft mainly to look at ice properties offshore, but there was atmospheric research components to that as well. And so I started thinking, well, perhaps there are opportunities here to use these platforms more frequently to get at some of the information that we really need to understand these clouds a little bit better. And this image shows kind of the variety of flavors of different platforms that exist way off on the left. So Holger referenced the fact that I was just out at the Shout campaign. This is at Edwards Air Force Base. That's me standing in front of the Global Hawk. That's one gigantic scale of airplane. And the footprint of that is maybe not ideal for doing these kind of fine-scale process studies. But as you move to the right side of the figure, you start to move down in scale and cost. And I really became interested in some of these smaller platforms, more on the right side here, probably starting with the Aerosol over. Aerosol is the one in the middle here. And these are things that are on the order of a couple meter wingspan or smaller. They're generally fairly lightweight. The operational footprint is generally fairly small. The cost can vary quite a bit. An Aerosol is not a cheap platform to use, but when you come over here to the DataHawks, this is an airplane that was developed on campus, and the Sumo, which is used by John Cassano for Antarctic research quite frequently. There you're looking at a cost of on the order of $1,000 for the airplane. And so I started thinking about how we can use platforms kind of on the right side of the figure here to get at some of this information, and that's kind of what I'm going to go over today. Some of the early efforts, I would say, at trying to do that. So the first platform that I became quite interested in is one that was developed on campus by Professor Dale Lawrence from the Aerospace Engineering Department. This is the DataHawk aircraft, and this picture shows the first version of that plane. This plane has about a 1 meter wingspan. It's quite lightweight. It's a total mass of 700 grams. As I mentioned, the vehicle parts cost is on the order of $1,000. Generally flies at around 15 meters per second. And this version of the plane had a duration of 45 to 50 minutes, which kind of has a fairly limited range, but for some of these measurements, that's okay. In terms of measurement capabilities, I'd say they're relatively basic. There's a temperature sensor on board, a slow temperature sensor on board, a relative humidity sensor, pressure sensor, and there's an estimate of the wind vector based on the airspeed measured on board and the position of the aircraft and the attitude of the aircraft. And then there's also a series of thermopiles on board, which for this specific platform were actually used both for navigation as well as for sensing. So this version of the plane was using the thermal contrast between the ground and the sky to know what level was supposed to look like. And so you'd go through this calibration procedure to kind of get used to the sky temperature versus the ground temperature. Some of you might be thinking this doesn't work very well in the Arctic, and you're absolutely right. And I'll get into that in just a second. So one question that always comes up with unmanned aircraft is the access to airspace, flight permissions, dealing with the FAA. And in general, people see that as a major hindrance to using unmanned aircraft right now for research. And I think that's somewhat fair, but I think that's going to evolve fairly dramatically over the coming years. And there are opportunities, and I'm going to get into this specific opportunity here, where there may be chances to fly these platforms in environments where the FAA is not the main governing body necessarily. And so this map up here shows a couple of Arctic sites, Red Barrow, which many people may be familiar with, kind of northern tip of Alaska. If you go about 265, I guess, kilometers to the southeast, there's Aliktok Point. Aliktok Point is an Air Force long-range radar station, and starting in 2004, the U.S. Department of Energy began working with the FAA to secure restricted airspace at that site, and that was for supporting tethered balloon operations. So they were interested in profiling with tethered balloons from the surface to look at pretty much some of the stuff that I had already talked about here, cloud properties, aerosol properties, turbulence, and dynamics. And so they set up this area of restricted airspace. This is R2204. It's centered on Aliktok Point itself. It's a 4 nautical mile diameter cylinder. It is broken up into 2 height ranges. The first one, I believe, goes up to 1,500 feet above sea level. The second one goes up to 7,000 feet above sea level. And that was established in 2004 and was used for the MPACE campaign, the Mixed Phase Arctic Cloud Experiment, and then was kind of forgotten about for a little while until the FAA came knocking to DOE and said, you guys have to start using this or you're going to lose it. And DOE, perhaps somewhat forward thinking at the time, said, well, let's figure out the best way that we can use this. And so they put plans into motion to put instruments in place on the surface. And so this is a view, maybe kind of small for people in the back, but from the rooftop of one of the ARM mobile facilities, which has been positioned at Licktuck Point for a 5-year period now, starting in 2013. That period may be extended. But anyway, you have these nice surface measurements in a location where you also have an ability to work with the Department of Energy to get permission to fly overhead. And so you can kind of start to pair the surface measurements with the aircraft measurements in this location. In addition, more recently, DOE worked to secure a warning area, and this is fairly new. I think this was approved about a year ago, and this extends offshore, so 10 miles from Licktuck Point all the way out to 82 degrees north. So you've got a 700 and something mile corridor that, again, with roughly the same altitude ranges, it actually goes up to 10,000 feet. But you can send aircraft into this warning area, which can be activated by the Department of Energy. And so this is where I've done most of my flight activities. Certainly, we had a small meeting just before the seminar here, I mentioned just because it's not dealing with the FAA doesn't mean that it's easy. We still have to get approvals from Sandia National Laboratory and Department of Energy to fly here. So it's not an easy road where you just show up and say, okay, I'm going to fly, you guys turn your airspace on. You still have to go through an approvals process. But that approvals process looks slightly different than what the FAA has in place at the moment. So the first set of flights that we conducted at Licktuck Point were somewhat of an engineering experiment. This was really a bit of a proof of concept. We went up with the DataHawk in the fall of 2014. This was October for something that was at the time termed the Coordinated Observations of the Arctic Lower Atmosphere, COALA. We were flying the DataHawk along with the tethered balloon, the Sandia tethered balloon. And it was an interesting set of flights. So this is me, and that's Jack Elston, who was at CU. He now owns Black Swift Technologies here in town. We were up there for 2 weeks, and we got quite a few flights in. The map at the bottom left shows the flights. They were constrained to a fairly small area, but we learned quite a bit in 2 weeks. And one is that when you're operating in the Arctic in the fall, the conditions are not your friend ever. No matter how good you think things are, it's really challenging. So with the plane that we were dealing with, I told you we were using this kind of IR thermopile attitude estimation. When you have a condition like this, the surface and the sky are roughly the same temperature, and so the plane can get confused quite easily as to which way is up. And we did have one plane go down because it flew into a cloud bank and lost its wits, basically, about which way it was supposed to be going. The other thing, it was quite windy, and we had some pretty major icing conditions while we were up there. This is just a pole that was at the surface, but you can see a nice 1.5-inch layer of ice that was forming on that. And so just from an operational perspective, we learned that it can be a difficult place to operate. One neat thing was that we were up there right at the period when the sea ice was starting to form. And so one of the things that we were interested in is whether we can get some information on the spatial variability of temperature across this gradient as the sea ice is starting to form and you transition from open water to an ice-covered surface. And so this is one single flight map, just an example. We were flying at low altitude. This is the altitude scale here. It goes from 0 to about 35 meters. And so this light blue is the flight that we were trying to conduct, and that was sitting in kind of the 10 to 15 meter range. And so we were flying the plane at 10 to 15 meters above the surface. And one of the things that we were looking at was the variability in the surface condition. So this is information from these thermopile sensors. And these are not calibrated, so I don't have temperatures associated with this here. But what you can essentially see is you have, over the land surface, you have a cold environment. Offshore here, these yellow colors are kind of a broken ice condition. So you have this land-fast ice that was growing offshore. And then the red is open water. So you're essentially looking at the surface temperature. And within that, you see these newly frozen lakes, which are somewhat warmer than the tundra around it. You see the runway itself, which is dark. So it's slightly warmer than the kind of snow-covered tundra around it. And we work to map the atmospheric temperature at this 15-meter level relative to those surfaces. And I forgot to mention when I talked about the platform that this plane flies with a set of 10-micron fine wires, so you can get a fairly fast response temperature measurement on board. Unfortunately, one of the other things that we learned about flying in this environment is that fine wires and snowflakes don't get along. And so as we were flying through precipitation, the wires would shatter almost instantaneously as soon as we launched. And so this map here is kind of based on the slower response temperature sensor. But even there, you start to see fairly small here. We've got 0.2 of a degree difference, but fairly small difference between kind of the colder land surface points and this open water points. So I would love to show you this figure with the fast response temperature measurements, but unfortunately we were not able to get that there. But you start to see this gradient. And so things like this start to get at the questions about spatial variability. We think about model grid boxes, what the scale is there, and it's certainly bigger than this figure is generally. And so if we have this land site coastal measurement that's producing temperature information that we use to validate models or improve models, develop parameterizations, how representative is that really of the kind of larger spatial scale that we're dealing with? And it's particularly obvious here because we have the coastal gradient, but I think even over just a land surface, that's a very valid question that you can start to address with these platforms. So I mentioned some of the struggles. This is actually a sensor that we had sitting on the surface. You see the ice buildup on, this is the housing for the cold wires actually. So they sit right in here. 2 points there. One is that we were flying in icing conditions at times, which can be quite challenging. The other is that the cold wires, again, were exposed to elements that were not very favorable for keeping those working very long. As I mentioned, we did have a couple planes land inadvertently, let's say. And we had some nice help from the oil industry in recovering the one plane that went down offshore as we were flying over the water surface. They're quite willing to support our efforts, which I found somewhat interesting, but it's great. I mean, I was happy to see that. And I really hope to be able to get back there at this time of year again with some of the information that we have, because I think we can really improve upon that first round of flights. So from there, the DataHawk evolved a bit, working, this is Dale working on the plane himself, as well as me kind of providing feedback on what worked and what didn't when we flew in the Arctic. So one thing that you might be able to see here in the photo is that there's now this little sphere sitting in front of the cold wire, the entrance to the cold wire housing. And the idea there is that we can deflect snowflakes around the housing itself while still letting airflow over the wires. And we have flown this in clouds and precipitation without any issues, but it was all liquid precipitation. So we'll have to try this again in snow, and I hope to be able to do that in a couple of weeks when we go up to Alaska. Some information on this plane. So the thermopile attitude sensing has been scrapped. We're now using an onboard IMU, which helps us in a lot of ways. One is that our wind sensing improves dramatically. The attitude sensing improves, and so you can, in development of this wind algorithm, that attitude information is fairly critical. And so when you have improved the attitude estimation, you also improve your wind estimation. It flies slightly faster, so we can handle slightly higher wind speeds. In this case, 15 to 20 meters per second. It's also, it carries more batteries, and so we can fly for an extended time period. Before we were flying 45 to 50 minutes, now we're looking at 75, which extends the range fairly dramatically. Again, same kind of general temperature, relative humidity, pressure, the wind vector estimate, and IR surface temperature. And just as an example for kind of operationally what this looks like, the launch for both of these platforms occurs with the bungee. This is just a silicone bungee, and hopefully this video will play. Yeah. So the plane is hooked up to the bungee, and you essentially let it go, and it's set up to activate the throttle after it achieves a certain ground speed, and then the autopilot takes over from there. The plane can fly fully autonomously from launch to landing if things go well, and generally things go well. However, at this specific site, I'll get into in a minute, we did have some issues with interference from the quite powerful Air Force long-range radar that they use there. And so we had some issues with the plane that were somewhat unexpected and beyond our control. But before I get there, I wanted to talk a little bit more about sensors. And I'll be honest and say that when it comes to all of the technical specifications of sensors, I'm probably not the person to ask, but I'll provide the information that I can here. This is a close-up of the sensor housing. So we have a slow response temperature sensor sitting on the board that's kind of covered by the foil tape here, as well as a capacitive relative humidity sensor. This is, again, the fine wire housing. This is what things look like without the tape on it. This is a somewhat modified version of that sensor. So the one that we've flown on the plane has side-by-side wires. The 10 micron wire sits between these prongs here. This specific sensor adds two other wires. So the idea is that we have a hot wire as well as a kind of in-between warm wire. And Dale's been exploring ways to get humidity information from this setup, and he's done some testing on that here in the building, along with Gordon and Steve Semmer. And just some examples, these measurements, of course, are not calibrated in terms of their output, and so we do the calibration based on our own kind of activities. So on the left, I'm looking at the voltage on the cold wire versus the temperature of the ambient air, and so if you were to fly this plane without any information on what the variability looks like in the atmosphere, you end up in a somewhat non-ideal situation where you're doing this calibration using the slow response sensor, where you develop this line based on temperatures that are measured by that slow response sensor, and you're looking at what the relationship is there. A much better approach would be to find two different temperatures that you can expose the sensor to. Because each wire is slightly different, you have to do this for each individual sensor board that you fly. But there, when we fly in the Arctic, it's actually kind of nice because outside is going to be cold and inside is going to be substantially warmer. And so you already have 2 points for that line just based on that, and you can work off of that. On the right here, we look at thermopile voltage versus a body temperature. So here we were using, this is a fairly crude way to do this actually, but we were doing it out in the field where we had a bath that we had set temperatures, and we had a calibrated IR sensor to measure the temperature of that bath, and we could point the sensors to it. And you see these linear relationships. And so this is the kind of crude ways that we've calibrated these, or gotten calibration information for these sensors. This past summer, we did some evaluation of the sensors as well, and that's something that I think can't be stressed enough. We have this kind of explosion of interest in using smaller, relatively low-cost platforms for atmospheric research, and oftentimes we don't do a great job of knowing exactly how well the sensors that come along with those platforms perform. And so one of the things that we were interested in doing for the DataHawk was to put them through a somewhat more rigorous evaluation. And so again, we worked with people in the building here, with Gordon McLean and Steve Semmer, and some others to get some testing done. We used chambers inside. We also did some side-by-side testing on the Boulder Atmospheric Observatory Tower out in Erie. And so I'm going to step through just some of the general results there. This is looking at difference in temperature in the chamber between the sensors on the aircraft and what the chamber was set for. And so we have these distributions. Each one of these represents a distribution of differences for a set test temperature. And a couple of things to point out. One, the red distributions are the slow sensor that we have on board, and then the blue distributions are the temperatures that we've retrieved or we've gotten from the cold wire, and the black is the same cold wire but filtered, post-processed filtered, to get rid of some of the variability that we see on that measurement. And so, generally with the slow sensor, we see an offset of roughly 0.3 of a degree across a fairly wide temperature range, at least thinking about what we might be exposing this platform to operationally in the field. Whereas the cold wire values vary, the offset there varies somewhat dramatically. If you're wondering what's happening here, we've actually saturated that specific sensor at the low temperature value. So that's not that the sensor is not performing well, it's just not set up to handle that cold of a temperature range. Some of this curve could very well be what we're doing with our calibration. But certainly there's information here that becomes fairly critical when we start making these atmospheric measurements. We did relative humidity tests as well, and so I'll walk you through what the different figures mean here. we tested the relative humidity at several temperatures. So from the left, 260K to 310K. And so that's what these colors represent. The top row of figures here is the raw measurements from at 10 hertz. And so we're looking at the DataHawk relative humidity. And that DataHawk relative humidity measurement requires input from what the temperature is that the sensor is exposed to. And so on the left, we're providing that temperature from the chamber temperature that was reported. And in the middle, we're using the actual DataHawk measured temperature from the board. And I would say in general, when you look at this sort of a curve across a range of relative humidities, it's a little bit troublesome when we think about trying to apply some sort of correction to this in the field. On the right here, we were looking at a different set of sensors. This is a set of sensors from IMET that are being used on the Coyote. Joe Sion operates the Coyote into hurricane environments. And so I would say that in general, that set of sensors performed substantially better than the DataHawk sensors did here. And we've actually since then set up the DataHawk to accept these sensors on board as well. And we're planning to fly those in April in the field. Another thing that comes up is sensor latency. So this is a series of profiles that was obtained during one day, August 9th, this past summer with the DataHawk. These are plots of temperature from the slow temperature sensor on board. And the colors are representing the time of day, so the blues are earlier than the reds. This is just 4 flights over one day. And you see there's an evolution in the general atmospheric state during that time. You have this inversion developing, but you also notice that there's this offset between ascent and descent of the flight, and that's just a result of the response time of the sensor. And we can confirm that when we look at the cold wire estimates of the temperature from those same flights. They fall more or less right on top of each other. And so one of the things that we were very interested in trying to characterize with the testing that we did here was the response time of the sensors. And this is, of course, fairly challenging to do, but we gave it a shot. And so this is, on the left, kind of the raw measurements. This is for humidity, relative humidity. On the left-hand side, for the chamber reported value, we had a LICOR in the chamber as well. So we were going on the assumption that the LICOR at 10 hertz was reliable. Water vapor density and relative humidity, and then the IMET value as well. And so for each of these steps in the chamber value, you'd have some instrument response that you see in the curve here. And if you look at the difference, kind of the slope, essentially, for each of these curves, if you look at the raw values, it's quite noisy, but if you add a low-pass filter to this, you do see very clear spikes where you have the transitions, so that you can mark kind of the start of the change in the value of the chamber to the end, start of the change of the next value. And so you can pull out these curves. And so we looked at response times at 63 and 95% of the kind of expected value. And we did it here relative to the LICOR because the chamber values, I think when I spoke with Gordon about this, the chamber value is more a reported value than the actual value at the sensors within the chamber. And so we started to look at what the response times look like. In these figures on the left, we have the temperature response times. On the right, we have relative humidity for different temperatures. And we have 63% response and 95% response, 63 being the triangles and 95 being the circles. The temperature we did relative to our own cold wire because that was the fast measurement that we had in the chamber at the time. And you can see that the 63% response of the slow sensor was on the order of about 30 seconds or so, and the 95 was substantially more than that, pushing 200 seconds at times in warmer temperature regimes. And the relative humidity relative to the LICOR, again, we can see kind of similar numbers in some ways. The 63% response was, again, on the order of about 30 seconds, and 95 was substantially higher than that. And I would say that these numbers, we can do a better job of analyzing exactly what these numbers are, but this was just a first look at that to see kind of roughly where things stand with the sensors that we're using. As I mentioned, we also did some field tests. So we set up both our, a version of our sensors as well as some kind of traditional sensor, so a Gill Sonic and a LICOR in the background there, as well as some slower Vizsla sensors that we would raise up to 100 meters above the surface on the BAO. And you can see the carriage, they're kind of sitting out on the boom here. And at the same time, we flew the aircraft on 2 separate days at the same altitude in a circular pattern just next to the tower. And one of the things that we're very interested in is whether we can use these aircraft to derive the turbulent surface fluxes. And so we started looking, in this case, for sensible heat flux at using the measurements of the wind estimate and the temperature, the fast temperature at 10 hertz to derive turbulent fluxes using the covariance technique. And so this is 3 different flights in 3 different sets of conditions where we have the vertical velocity anomaly, let's say, in the top row, with the green line being the values from the plane and the orange from the sonic. This is potential temperature, and then this is the product of the 2, and then the derived sensible heat flux over time. And you can see on the left-hand side, there's a bit of disagreement between those 2. This was a condition where we had very little wind. It was very quiet. And in general, these measurements don't work very well with a low wind environment. And that's true for the airplane as well as kind of the surface or ground-based measurements. Moving to the right here, these 2 were from the second day where we had a bit more wind and things converge a little bit better. So this is early on where the sensible heat flux is increasing with time over the length of the flight. We also looked at the spectra, and there are some kind of things that we're not quite sure about here. For one, we've got this kind of low frequency spike in the vertical velocity, which is likely something to do with the orbit of the aircraft. So that's about the orbit time of the aircraft, and it seems like that spike would map on one orbit. And so there's something there where our wind estimate is still sensitive to where we are on the orbit. The other is we've got this strange spike in the temperature, which shows up fairly consistently, and that's something that Dale and I are trying to figure out right now. We're not quite sure what that is. But this was a nice way to demonstrate that it seems like we're at least moving in the right direction to try to do this in the field. And so we took this plane back to Alaska, or up to Alaska for the first time this past summer as part of the ERASMUS campaign. ERASMUS stands for Evaluation of Routine Atmospheric Sounding Measurements Using Unmanned Systems. And the plan was to fly hourly profiles with these planes where we have one ascending profile and one descending profile, and one of them is onshore and one of them is offshore, so we get some variability over the coastal gradient. And so we'd fly to the top of the airspace up to 2 kilometers in cases where there were no clouds, and in cases where we had clouds, we would fly to cloud base and back down. That was the plan. However, as I mentioned, this thing became our arch nemesis. There are 2, actually, high-powered radars there that are used by the Air Force and the FAA for traffic detection and other detection. And our plane was not equipped very well to handle the energy coming from that system. And so we ended up slightly handicapped in that until we had the plane set up in a way where we knew we could always take it back over, we were very limited in what we could do from a flight perspective. We also had some bears around, which is not fun when you're trying to fly a plane and your focus is up there and you know there's a bear coming nearby. So that also disrupted our kind of plan to profile hourly. But the idea was really to kind of come up with a solution for this sort of a problem where you have, if you're looking at radio soundings, for example, and you have a transition from a clear to a cloudy atmosphere and you're trying to understand what's going on there thermodynamically, this profile and that profile look very different, and if you're lucky, you might have one in the middle somewhere. But it's very rare that you have good resolution right at this transition time period. And so we were hoping with hourly profiles to be able to fill in some of that information. And this is just a plot that shows the profiling that we did do over 1 week here. You can see kind of where the clouds generally were and where our pilots felt comfortable going to, given that we were concerned about the interference from the radar. And so you have here kind of relatively continuous temperature profiles given the crew that we had, for a 1 week period. And so you start to fill in some of that information on how the atmosphere is evolving temporally. If we zoom in on that a little bit, this is an example from one single day, and we had a bit of interesting activity. We had kind of this cloud layer that was forming and dissipating at a height of about 150 to 200 meters. Eventually, an inversion also set up right in that same altitude level. And so this is sort of just an example of some of the information that you can start to pull out of this kind of frequent profiling with relatively low-cost equipment. You can also start to look at the near-cloud environment. This is a case where we had these fairly thin, wispy clouds that would kind of form overhead and dissipate and form overhead. And so for this specific flight, you can see this was a flight of roughly a half hour. This is the cloud base that was observed from the arm-ceilometer at the time, and we were flying kind of right along that cloud base to try to profile the thermodynamics in that environment. So this is equivalent potential temperature right in that area. Going back to this figure, I also mentioned that radiation and aerosols are quite important, and it's important both for the formation of the cloud as well as understanding what the ultimate radiative impact is. So just as an example, I'll put both of these up. This is an example where we have, we're looking at long-term statistics of cloud emissivity relative to the pollution levels. So we're thinking about how the aerosols are impacting the cloud microphysics and changing the long-wave emissivity of the clouds. And so on the left here, you can see there's a shift both in the size of the droplets retrieved as well as the kind of radiative impact here. And on the right, you can see for given liquid water path ranges, those are the different colors, so 5 to 10, 10 to 20, 20 to 40, and 40 to 80. There's kind of the separation that occurs in the emissivity of the cloud based on whether it's a clean condition in the thin line or polluted in the thick line. And so we start to worry about or think about how we can observe aerosols. And just as one other example, on the left are radar-derived products that were taken during the ASCOS campaign. This is the Arctic Summer Cloud Ocean Study, which was on the icebreaker Uden at about 88 degrees north. And we again have this single layer liquid cloud. So this is the liquid portion of the cloud, precipitation falling under it. And the radar, it's a Doppler radar, so we can start to get information on the dynamics, the local dynamics, the cloud-driven dynamics. And this figure here is the one I'd like you to focus on. This is the turbulence dissipation rate from the radar. And as we look initially, you can see that there's a fairly stark transition here from low turbulence dissipation rates to higher. And this is representative of a decoupled cloud state where the cloud mixing is not extending all the way down to the surface. There's no surface-driven mixing. And so you have this kind of layering of the atmosphere. And then later on, the cloud does mix all the way down to the surface. And I've got those three dashed lines on there. Those are related to time periods when there was a helicopter operating that was making aerosol measurements. These are profiles of the aerosol concentration at different size ranges. The important part to pick out, this is early on in the period. That's the first dashed line. You can see there's a gradient here from the surface to the cloud depth. Interesting that the different size ranges have that gradient going in different directions, but that's a different question. And so you can imagine if you have this surface aerosol measurement, you're trying to understand how those aerosols are impacting the cloud, you may be getting misinformation if you're trusting that that's relevant for the cloud at all. And as the time period progresses, you go to the second dotted line and the third one, you can see that those gradients are kind of mixed out, and then you have a much better mixed profile. And so one of the other things that we're interested in pursuing is how we can do that with, again, unmanned aircraft. This is the CU Pilatus. This is a somewhat larger airplane. For scale, you can see some people standing in the background, but the wingspan here is about 3.2 meters. And we've instrumented this with a variety of different things. On the wing out here, we have a pod that holds Terry Hoek's sensor, the pressure, temperature, humidity pod. In addition, we are borrowing instruments from the Pacific Northwest National Laboratory for radiation measurements. So we have, in the big picture here, we're using Delta T, SPN1, Shortwave, Broadband pyranometers. And then in the inset here, we can replace what we have with long-wave instruments. So that's this Kippen zone and CGR4s. And we also have this printed optical particle spectrometer, which was developed by Rishon Gao at NOAA CSD. There's an inlet out on the wing. It takes aerosols in, and we get an aerosol size distribution from that. So I'm going to just briefly touch on these things. The SBN1 covers 0.4 to 2.7 microns, has a very fast response time, which is quite important for airborne measurements because you're moving quickly over various surfaces, and you're coming in and out of cloud cover, for example, so you want to be able to capture those boundaries. It also features the shading pattern, which allows it to provide an estimate of the direct and diffuse portions, which is somewhat important because, as I'll get into in a second, we have to, of course, account for the attitude of the airplane. Its measurement is very sensitive to the angle relative to the sun. The CGR4s are 4.5 to 42 microns, a slower response time, and a very wide field of view, which for ground-based observations is great. For aircraft, maybe not the best, and I'll show why in just a second. So thinking about the attitude stuff, this is an example of measurements that we actually took from a car top platform, and I'll tell you why we used the car in just a minute. But we can see the evolution of the shortwave irradiance as time goes on during the day, from about 7:30 in the morning to a little after noon. And maybe at first sight this looks reasonable, but if you look at theoretical values, we have a lot of things that are above what they should be, and that's because the aircraft, or the car in this case, has motion relative to the sun. And so as you point the sensor more directly into the sun, you have a stronger radiance, and then you're exceeding what theoretical level radiation is there. And so we have to perform this offset characterization. What we do, this is our car top setup. We've got two Delta T SPN1s, and we're trying to characterize the offset of those instruments relative to an INS, which is co-mounted with the instruments. And so the INS will help us to correct for the attitude relative to the sun, but first we have to be able to characterize how level the instruments are relative to the INS, because even small offsets there are important. And so we drive using the car over a loop. I don't know if we have cyclists in the audience, but if anyone is, can you tell me where this is? It's in Boulder, I'll tell you that. Or, well, right on the edge of Boulder. This is Lookout Road, right in 75th and 76th. So you get nice topography there. And so we have these sensors on the car. We drive, get a variety of pitch and roll angles, turn the plate so pitch and roll vary. And so there we characterize the offset. And then we use that to, using a technique developed by Chuck Long, who's now at NOAA as well, we correct for attitude. So the corrected values, now you don't have this gross exceedance of the theoretical maximum. You still have issues with shadows and clouds and things like that. But and then we can apply that information, that correction, to, in this case, aircraft measurements. Here we've plotted the irradiance, uncorrected irradiance, as a function of the tilt angle on the vertical axis and the aircraft heading on the horizontal. This is then the adjustment that comes out of the correction algorithm, and this is then the net product where you see this gradient is kind of eliminated through that correction. And so we can use that then in flight. Here's an example where we had two flights, which is the kind of noisier areas here are from the aircraft. This is a surface-based measurement that was about 20 miles away. Just as a comparison between the two. We can look at the downwelling, upwelling, and the net radiation of the plane. We can also look at, in terms of the downwelling component, we can look at the total direct and diffuse components coming in and use that information to come up with information on things like surface albedo. Here we have two flights that were completed in Arvada. It was an interesting day because when we first started flying, we still had some snow cover on the ground. And this was in April, and it burned off, melted pretty quickly. And so the first flight, which was earlier on, about 10:30 in the morning, we had a substantially brighter surface than we did later in the day. Later in the day, we only had the bright concrete runway to kind of increase our surface albedo values. Looking at the Longwave, again, similar idea, except not quite as concerned about the correction, but this is where that 180-degree field of view becomes problematic, right? Because the minute the airplane starts turning, you start to see the surface and vice versa. And so you see this kind of cyclical pattern. This is related to our very tight circle that we had to fly when we were flying in Arvada. And that's also the reason that we do this offset characterization using the car, because we don't have the airspace in Colorado to fly long level legs that might be necessary on a clear day to do it with the aircraft. Very quickly, the aerosol side. So this is printed optical particle spectrometer, as I said, developed at NOAA Chemical Sciences Division. It provides size distributions for particles from 140 to 3,000 nanometers. And we did do, you can see some specs on the weight and the size of the unit. If you want these details, please come find me afterwards. We did some calculations on the kind of sampling efficiency. And so you see that for the Pilatus, at least, with the way that the inlet is set up and the tubing extending from the wing to the sensor itself is set up, we do have some oversampling of larger particles, but it's something that we can take into account when we actually look at the size distributions that we obtain with the instrument. Here we have 3 different flights that were all taken within a couple hours of each other, so there's not very much variability. But certainly in the Arctic, we're interested in looking at both the vertical variability of these size distributions as well as the horizontal and temporal changes. And so we are taking that platform to Elictoc in just a few weeks. The first 2 weeks of April, we'll be flying there, and we're hoping that we can catch the end of the Arctic haze season to look at the aerosol during that time period, and as well as the radiative impact of those particles. And our plan here is to fly kind of an elongated box pattern. This is roughly 2 kilometers, and we'll climb up to our maximum altitude, and then either fly level legs and descend on the way down, 1 leg at a time, or we may actually just go slightly nose down the whole way, which is, from the radiation perspective, not all that different. It keeps the sensors fairly level to the ground and is slightly more efficient from an energy perspective. All right, to summarize, we're developing and testing a variety of unmanned aircraft for high latitude atmospheric research and kind of surface atmosphere interaction research. The DataHawk and DataHawk 2, which were developed on campus, have been deployed to Elictoc. I should mention that the Department of Energy ARM program has actually purchased 4 of these DataHawks, the DataHawk 2, and they plan to start deploying them as well. There will be a community facility through the ARM program. The Pilatus is equipped with a variety of instruments that stem from efforts here in the building at NCAR, from NOAA and PNNL. And this platform will be deployed to Elictoc in just a few weeks. We're right in the middle of all the preparations for that. We recently, this last summer, completed efforts to try to understand the performance of the sensors. I think there's more work to be done there in general, not just from our sensors, but as a community. I think we have a lot of work to do in really understanding how well these things perform on the small platforms as well as the larger platforms. Turbulent surface fluxes appear to be an interesting target for these smaller platforms, and we're trying to work towards feeling confident that our platform is reporting similar values to what would be observed using kind of more traditional surface-based tower measurements. And I think there's substantial potential for our systems to provide information on spatial variability, both horizontal and vertical. I will stop there. Acknowledgement of our funding. A lot of it has come from the DOE programs, ASR and ARM. NOAA, of course, has supported our research series through the Innovative Research Program, and the National Science Foundation as well.
Okay, thank you.
A quick view.
Very, very interesting. Before we open for questions, I forgot one very important point in the introduction. Gijs just received a Presidential Early Career Award, just a couple weeks old, so do want to congratulate him for that as well.
Thanks.
Any questions?
What kind of typical roles are we talking about in terms of these aircraft? Have you ever considered physically correcting the
You mean in terms of having kind of a leveling platform on board? So the short answer to that is the roles depends on the airspace, right? When we fly at Elictoc, we hope to have a lot of level legs because we have more space available to fly in, and we can make the turns very gradual if we want to. When we fly around here, we're usually constricted to lower altitudes, visual line of sight, smaller areas. The FAA kind of dictates that we stay within a small area, and there we have pretty high bank angles because of the fact that we can't go very far. I would say that generally the physical attitude correction has been too heavy for these platforms. I know, for example, Anthony Buchholz at NRL has developed a pretty nice system to keep broadband radiometers fairly level in flight on larger manned aircraft. Something like that would be way too big and way too heavy for what we're operating with here. As an example, for the Pilatus, that plane right now, fully instrumented, is about 50 pounds. And when we're talking about the payload, it's a fraction of that. So then we're talking on the order of 15 pounds or so, depending on how much battery we'll want to include, and that impacts our flight duration. So yes, I have considered it, and I haven't found a good solution. But if you know one, I'm happy to talk more about that.
Right back there first.
Is there any hope for aerosol measurements on the DataHawk platform in a smaller package?
Yeah, I think so. Maybe the DataHawk is interesting. I don't know that you have to go that small necessarily. For example, Rushan Gao is right now looking at an X8, which is a glorified DataHawk. It's a slightly larger version, but he's putting pops on there along with a filter sampler and one other instrument. I'm blanking on. It might be an ozone instrument actually, because he's looking to send that up as a glider, so balloon launch it and release it at a higher altitude as a glider and have it come down without propulsion. His hope is that then the FAA is not so picky about it. I'm not sure that will be successful, but maybe that's true. If it is true, I don't know how long it will be true. Yeah, I mean, I say that somewhat jokingly, but it is an obstacle at this point that we have to deal with, working within the rules that are provided by the bodies governing the airspace. And so I say that trying to find ways to work within those rules but bend them or extend them a little bit is not a horrible thing. I think that's a good way to try to get the maximum measurement that you can. In terms of doing it on the DataHawk, I think it's perfectly feasible, but I don't know that it's necessary. There are other low-cost platforms that could be used potentially.
Harry.
What's your flight durations you're hoping for this spring with the Pilatus?
If we use the heavier payload, which is the SPN1, so that's the heaviest version we have, I should mention, I don't know that I did mention, but with that plane we have 3 configurations essentially. One is just flying the PTH plus the POPs and extra batteries. And then the other 2 configurations are that with less batteries plus the CGR4s, or that with less batteries plus the SPN1s. With the heavy payload, when we were flying here in the spring last year, we were achieving about 25 minutes, which is fairly limited. Without having the radiometers on board, we can hopefully double that, so fly about 40 minutes with the POPs instrument and the thermodynamic measurements.
So do you think will the duration improve any, just because you'll be at sea level versus altitude here? The airframe would probably be a little more efficient.
Maybe a little, but we're also operating at much colder temperatures, and so the batteries are impacted by that.
That would be a big impact.
Well, it's hard to say. I mean, those batteries are very large, right? We're looking at 6L bricks of about this big. There's a lot of self-heating going on. Our plan is to keep them at a warmer than room temperature value until we put them in the plane. So hopefully they can maintain a lot of that heat by the time we launch. But we just have to see. It's really hard to test that here. I can say when we flew here, we were flying in conditions that were around 40 degrees. And when we fly to Lake Talk, we'll likely be in the kind of 10-degree range. But the other thing about the Pilatus is it's by no means an ideal platform, right? It's the plane we had, and that's what we worked with. It was the plane that we had that could carry the weight we needed it to. There are definitely better solutions that are more efficient. One of the things that we did with the Pilatus when we first started down the road of instrumenting it with the radiometers and the POPs is that we changed from gas to electric propulsion, which is not working in favor of extending the duration, but it is working in the favor of alleviating concerns about carburetor icing and alleviating concerns about polluting our own measurements. So there was a clear trade-off there.
Do you have any communication with the aircraft in flight to get data as it's going, possibly change flights or
Yes.
up and down?
Yep. Yeah. So both of the planes all of the planes that I talked about here can fly autonomously, but we have constant radio communications with it, and we can change the flight patterns. We do stream data down from both planes, so not all of it from the Pilatus, but enough that we know that the sensors are working. And so yeah, we can make real-time adjustments to the flights and to where things are.
Would you sacrifice stability or range for, airspeed for a better stability, a more stable platform?
You mean would I fly faster or slower?
Yeah, exactly. Well,
Or either?
Either, yeah.
Got it.
How important is stability versus speed or range?
I think for the DataHawk, the stability is not critical. You want it to be as stable as possible because if you're bouncing all over the place, it's going to be really hard to get an accurate wind estimate. And accurate in that sense is kind of a loose word, I think. I think that we need to evaluate that a lot more closely than we have. For the radiation measurements, the stability becomes fairly critical. And there, I think, a couple of things to consider. One is the response time of the sensor. So for the long wave measurements, we're looking at an 18-second response time. In theory, there's not going to be a ton of variability there in terms of what the temperature of the structures that are above and below you are. For the shortwave, we have a much faster sensor, and so there the speed becomes somewhat less critical because you're probably resolving the changes fairly fast enough anyway. So I guess my answer is I would trade if I can make the platform more stable by flying slower or faster. I would certainly consider doing that.
So have you ever tried to concurrently launch multiple things together and get different patterns or different levels at the same time?
Yes, the DataHawk. So last summer when we were flying at a Talk, we did attempt multiple aircraft flights, and that's very doable. But when the radar is interfering with your airplanes, it was a nightmare to try to keep one flying, let alone two. We did have a time, so we tried this towards the end of the campaign because we thought it would be an interesting thing to do for many reasons, and we timed it with a radio sound launch. So we could fly two platforms at two different heights, have the radio sound launch past both of those heights, get good sampling statistics at both of the altitudes. But the time period that we were able to keep both of the airplanes operating for was relatively short because we would be hit with interference, and that was it was really debilitating in a lot of ways. I'll be honest. What ended up happening, so that it kind of becomes clear as to why it was a problem. For the DataHawk, we have one central microprocessor that handles both the autopilot as well as the sensors, and that was getting completely locked up by the interference. And so for our first flights, before we were able to put a multiplexer in place that we could always grab it manually and bring it back down, we had planes that were at a kind of consistent bank angle because they were doing a local circle, and the microprocessor would lock up and the plane would be in that bank angle until it kind of became unstable and came out of it, right?
Would those conditions a little bit better in Barrow if you try that?
Yep. So Barrow also has a long-range radar. The Air Force has one there as well. There's a whole network of these. But the bigger problem in Barrow is that the FAA doesn't like us flying there. They have the airport that's right there. And the arm site in Barrow is right on the approach to the Barrow airport. So the FAA is not very happy with the idea of flying over the arm site in Barrow. But there are groups that have flown in Barrow, and not at the arm site, but offshore. So they launch from Gnarl, if you know Barrow, and then head offshore. This was to do whale surveys last year with Scan Eagle UAS.
Any other questions?
Have you attempted ways to mitigate the radar issue, or what?
Yeah. So in fact, when we go back up in April, we're going to take the DataHawk with us as well and test whether that works. It's really hard to recreate that problem here, but basically, what we found is that the most likely solution to work would be being able to support in-flight reset of the autopilot. In principle, that seems straightforward, but in practice, you have an initial calibration that you do for the aircraft in terms of the attitude measurements, things like that. And so having the autopilot completely power off and power back on and not lose something critical. We think we've done that, but we'll find out when we go in April. So in theory, if you can store enough stuff in a place where powering it down won't matter, you can quickly grab those constants back and have the airplane functioning appropriately again. But until you test that in real life situations, it's really hard to say that it's all been done correctly.
Is there any shielding that can work?
We tried. When we were up there, we were trying. We got as much aluminum foil as we could possibly find. We don't have a lot of weight tolerance there, of course, so the shielding that we would be putting in place would be lightweight. It's not to say it can't be done, but we didn't have any success. And the other issue, of course, is that you still have to have sensors connected to that, and you still have to have communications with that autopilot board, so you can't totally isolate it. You can do your best, but at some place there may be something getting through. But we do think that we've certainly implemented a solution that will hopefully take care of the issue. And find me in May, and I'll tell you whether it did or not.
And what do you think was causing the problem? I mean, is it stray voltages that are getting in there? I mean, what does the interference do to you?
What does it do to the plane?
Yeah, how is it interfering with you? It's an S-band, I guess.
We have very little information on that radar. The Air Force is not really happy to share all of that with it. I'm sure it's out there somewhere, but we don't have a clear set of information on what the scanning patterns look like. I think it is S-band. I think we found what the frequency is, but what it did to the plane is that it would lock up the central microprocessor, and that was due to something getting in. How exactly that was happening, I'm not sure. It's beyond my general knowledge, but there's some folks on campus on the engineering side that we're looking into that, and they think it has to do with one of their buses, the communications buses, causing issues. Yeah.
Okay. Any pressing last question? If not, then thank you very much, Gijs.
Yeah, you're very welcome. Thanks for having me.